We are going to be discussing acids and bases, but before we can discuss them, we need to look at the process of dissolving in water or any solvent a little more closely so we understand what's going on, okay? Dissolving, what does that mean? Now there's two words that we sometimes use. There's dissolving and then there's dissociating. Dissociating. They kind of mean the same thing. Whoops, I think there's only one S in dissociating. Okay, dissociating. No, maybe there is two S's. Just like association or associating has two S's. But if something is going to dissociate, that means if two people are friends and they dissociate, it means they break apart. They no longer are friends. They get away from each other. To dissociate means to come apart. Associate means to bring together, right? If you're associated with something, it means you're joined with it somehow. So dissolving and dissociating. Now, some people argue that these are two different things, and some people argue that they're the same thing, and it's kind of a bit of what we call semantics. It's a little bit of a name game. But we'll look at the process in general, and then we can decide on what word we're going to use to describe it in chemistry. So here's the deal. First of all, in order to dissolve, you have to have a solvent, right? That's the liquid. Usually it's a liquid. I shouldn't put liquid because it doesn't have to be a liquid. That's what's weird. You can dissolve things in a solid, and you can dissolve things in a gas. So it's a substance, let's put this down, a substance in which things are dissolved. Okay? And then the solute is the word we use to describe the stuff that is dissolving in the solvent. The stuff dissolving in the solvent, okay? All right, so what makes something dissolve? Why is it if I drop a nail in a glass of water, it doesn't seem to dissolve, but if I pour in salt, it does seem to dissolve? What's the difference? And it all comes down to the miraculous nature of water. There's this cool thing about water that we're going to discuss. Now, this is a discussion about water in particular, because water is a very common solvent. It's one of the most common solvents that we use. In fact, it's often called the universal solvent, right? But there are other solvents. We often use the word solvent to describe sort of harsher chemicals that we use, like paint thinners and varnishes. You can clean them with solvents. So sometimes we think the word solvent is something kind of nasty and bad, but it isn't. They're called solvents because they dissolve. Paint thinner is a solvent because it dissolves paint, right? Acetone can be a solvent because it dissolves greases and things. So the word solvent just means that things will dissolve in you. Anyway, let's talk about water as the universal solvent, okay? Because in chemistry, very often what we're doing is we're dissolving our stuff, our chemicals, in water. Now, why is water such a good solvent? Well, I'm going to tell you why. But we're going to have to look at a water molecule. So, remember how we learned that if you take an oxygen molecule and you draw its Lewis dot diagram, you get this kind of structure. There are 6 outer electrons around the oxygen in its outermost orbit. And of course, if we take hydrogens, which have 1 electron, they can sort of get lined up here, and we can see that they can share a pair of electrons here and here. And so the picture we get, the Lewis picture that we get, is looks sort of this way. It looks like a 90-degree bend, okay? But that's not actually true. On the flat surface of the board, it might be that might be the way we draw it. But when we look at it in 3 dimensions, we have to imagine that all of these electrons, so these two, and these two, they're little blobs of electrons that are negative, and they all push away from each other. That causes the bonds to kind of stretch out in a 3D way. And if we stretch it out in a 3D way, what we find is that the oxygen sits in the middle. One of the H's sort of goes back into the black or into the whiteboard a little bit, and the other one sort of sticks out. So I'll draw them at a bit of an angle. And then the other two electrons, that like the ones that are not shared, we draw them here and here, but again, one of them is sort of sticking further out towards the front and one is towards the back. Very hard to draw a 3D thing on a flat surface like this. But the key for us is that this is more what it looks like. It's a weird bent water molecule. So we always draw it with a bend like this. This is how I draw them. And remember, I don't often put these guys in, but we remember that they're there. So it's not quite a perfect square corner. It's actually, I think, about 107 degrees or something like that. But that's really not the most important thing. The most important thing is to remember about polar covalent bonds. So remember that along this bond, oxygen is more electronegative, which means this shared electron spends more time around the oxygen than it does around the hydrogen. And the same is true for this one down here. This bond, this shared pair, those electrons are usually over by oxygen, and they're only by the hydrogen a little bit. It's a bit of a hog, oxygen is, right? And so what that means is if we draw this picture again, and I'll just draw it simpler, that there's a sort of a line we can imagine down the middle of the molecule like this. And on the oxygen side of that line, that's where most of the electrons are usually around, which means they get, remember, they get this little sort of charge, not really a full charge because we haven't lost or gained any electrons, but they're not evenly spread out. This is kind of like if you imagine a room full of boys and girls, okay? We could have boys and girls all just sort of mixed around the room, and they're all running around. We'll have the same numbers of boys as girls. There's 3 boys and 3 girls. We could do more, 4, 5. It's kind of just random. They're all walking around. But it is possible that all the boys and girls might be sort of lined up on one side. The girls are all talking and the boys are all talking. Like this. It's still the same number of boys and girls. So if we consider boys as positives and girls as negatives, there's no charge. It's still even Steven, right, in the room. But look where they're standing. The boys are sort of all on one side, which makes this a little more positive and makes this side a little more negative, even though it still adds up to 0. So this is something we could call this like a charge separation. That's another way to think about it. It's a neutral charge that separates and gives sort of the appearance of having a plus side and a minus side, even though they cancel out. So that's what's happening here. The electrons are moving over to the oxygen side, and they are making one side a little more negative. It's like all the girls were on that side. And this side where the hydrogens are is a little more positive. So we use these little sigma, Greek S's, sigmas, to show this polarity. This is called a polar molecule. It's a polar molecule. It has 2 distinct poles or different spots, one that's more negative and one that's more positive. And it's all because of this polar covalent bond. It's all because oxygen wants to hog the electrons. Now, let's think about what happens when we take something like sodium chloride or salt and we put it in water. So let's go down here. And let's just look at maybe one sodium chloride molecule, okay? So let me draw a little ball like this. There's the sodium, and it's attached to a little red chlorine, like that. Now remember how they got attached, right? The sodium gave its electron to chlorine, and it became a positive ion. And the chlorine took the electron and became a negative ion. So chlorine has a negative charge. And so and sodium has a positive charge. Now, what would happen if you put them near a water molecule? Well, if I put a water molecule here, right? Actually, let me change the shape of that. Sorry. Let me put a water molecule over here like this. And let's put another water molecule over here, sort of like this. Okay, let's remember that the water molecule has that strange, whoops, that was supposed to be blue. The water molecule has that strange nature of being polar. So there's a negative side over here and a positive side over there. And the same would be true with this one. There's a negative side over here and a positive side over there. Well, look what can happen. The negative side of the water molecule is negative. It begins to be attracted to the positive sodium ion, and it gives it a pull. It starts to kind of like, oh, I'm attracted. And the water molecule, that side of it, actually starts to pull the sodium. Over here, the positive side of this water molecule is attracted to the negative chlorine, and it starts to pull the chlorine. Now it's a tug of war. So the question becomes, what's the stronger pull? Is the sodium chlorine attraction stronger and it'll just stay together? Or is the water attraction stronger and it'll pull the molecule apart? For salt like this, for sodium chloride, the water pull is stronger than the ion pull, and it pulls the two apart. And so if you have a whole bunch of salt in water, here's what you end up with. You end up with a bunch of sodium ions that are positive, right? And they get surrounded by water like this. The water surrounds it. And of course, you have to think also 3D. This is just 2D, but even in front and behind. And you'll notice that on this picture, let me use red here. You'll notice on this picture that it's the negative side of the water molecule, the oxygen side, right? The negative oxygen side that is surrounding the sodium positive ion, because they're attracted to each other. Negative and positive are attracted. So the sodium is pulled away and immediately surrounded by water, so it can't join back up. And the same thing happens to the chlorine ion. The chlorine ion, which is negative, gets surrounded by water in this way. The water surrounds it sort of the opposite, in the opposite position. There's my waters. Because those waters have, this is the positive side of the water, isn't it? The H side is the positive side. And those positive sides are attracted to the negative chlorine, and they surround it, and they pull it off. First of all, they pull them apart, and then they surround them. So what dissolving means is that you have the ions pulled apart, and they're all held apart in the water, one ion at a time, surrounded. And because one ion is so small we can't see it, it looks like it disappears. That's what we say. It dissolved, it's gone. But it's not gone. It's just been all pulled apart so that and surrounded by water by this really cool thing that water can do. Now, here's the other cool thing about it. When they're pulled apart, they don't go back to being regular sodium and chlorine. When they're pulled apart, chlorine keeps that negative charge. It keeps the electron that it took from sodium. So this is not a chlorine atom, it's a chlorine ion that has been surrounded. And sodium stays positive because he doesn't get his electron back. If they gave the electron back, they would both be neutral, and then water wouldn't pull them at all. And that's why salty water still tastes like salt, because the salty taste is because it's ions. In a piece of salt, the ions are what make it have its properties of being salty. If you just had sodium and chlorine atoms, that's a different thing. Chlorine is a deadly poisonous gas, and sodium is a highly reactive metal, right? But when they're ions, they act completely different, and they just make stuff taste salty. So that's what dissolving means. Now, in the case of other things, maybe this pulling of water is not strong enough right here. Maybe you take another thing. Sometimes barium, things that are joined with barium don't dissolve very well because they pull together too strongly and water isn't able to pull them apart. So it all comes down to who's got the stronger pull. Is it the polar end of water that pulls on the ion? Is that stronger than what holds the ions together? Or is the ion being held together stronger? And that's why some things dissolve and some things don't. But a lot of ionic compounds do dissolve because water does have a pretty strong pull, and it can dissolve a lot of things. Okay? And so what we call this process is dissolving or dissociation. We say that the ions are dissociated from each other, but they're still ions, and they still act like salt. They still act like as if they were together. It's the same taste, the same properties, and everything, because they're still holding on to the electrons that they've stolen or given away or whatever. So that doesn't change. Okay? So that's what dissolving is. That's what water does. It has this cool ability. And that ability means that what water can do, think about this now. If you just have sodium chloride stuck together and you want to get a reaction, let's say you want to react it with magnesium fluoride, well, how do you get them apart? Maybe they're just too happy. But you put them in water, water will pull the ions apart. And now, maybe they might get together and rejoin in another way and start a new couple. So water is kind of like the great relationship breaker-upper, because it pulls the ions apart, which increases the chances they might combine with someone else. Right? And when they do combine with something else, okay, if that's something else that they combine to, if that has a stronger pull than the water, then it'll form a solid in the solution and it'll settle to the bottom. We call that a precipitate, right? A precipitate. Remember that from grade 9? A precipitate. So sometimes things get pulled apart and then they can rejoin in a new way that's stronger than the water pull and make a new compound that precipitates from the solution. So now we have a better understanding of what's going on. Okay. So what we have is a chemistry notation. If we want to talk about salt in your salt shaker, right, NaCl, then we basically mean, we call it solid. We put a little S here, solid salt. But if we want to talk about salt that's actually in a solution of water already, all right, so this salt that I'm talking about is basically, let's go up. Where is he? Right here. It's this sodium chloride stuck together. But what if we want to describe this sodium chloride pulled apart in the water, dissolved? We need a way. So what we do is we use a word, you know the word aqua, which means water, right? So we use the word aqueous, A-Q-U-E-O-U-S, aqueous, and that means dissolved in water. And so we put the little AQ here that I showed you before, and that little AQ tells us that we're not talking about salt in a salt shaker. We're not talking about little white crystals. We're talking about this purple circle here. We're talking about salt that's been put in the water. It's been dissociated in the water, and all the ions are separate from each other. That's what we mean by AQ. And that means that this salt is now ready to do something because those ions are pulled apart and now they can join with other things. It kind of makes the sodium chloride more active, right? So that's what AQ is, and that's what dissolving water is. And when we talk about acids and bases, they pretty much always have to be dissolved in water, so this little AQ is going to show up all the time. Okay. All right. That's all we'll do for there. When we get to the acids and bases, we'll show how they dissociate in more detail.